Hello, welcome to a new lecture on state space representation on state variable formulation. Those of you who are new to the channel can kindly subscribe to the channel. So yeah, let's start with the state space modeling. So just like the transfer function modeling, we had the transfer function model in the form of R of S, and then we had the comparator signal J and K, then we had the plant in form of G of S, and we had the final output in form of C of S, which was being compared with the help of a transducer, which was the feedback element, with respect to the comparator. And this variation of gain K gave us the stability and other things. So here there is another form of a representation of the system that is called the state space form. The state space form. So in the form of representation, state space form, or we can in other terms say state space model. In the state space modeling, what do we do about? We write an equation in form of x dot is equal to ax plus bu. I'm going to explain you everything. Don't worry about that. And similarly, I write y is equal to cx plus du. So here in see the first term x and the second term you can see is x represents the state vector, whereas x dot represents here x, x dot represents here the differential vector. So differential vector, yeah, these are the terms you have to remember. This is the differential vector basically. So what happens is that u and y, as you can see, are acting as input vector. Okay, this u term is acting as input vector, and this is the input to the system that is given, and y here primarily y is acting as the output vector. So vector is a quantity which is either a column vector or a row vector. It is having either a column, it can be vector, it can be in this form 1 or 0, or it can be 1 0, or either it can be one row, okay, into two columns, or it can be, you can see, two rows into one column. So this is the vector quantity. What I mean by vector, so you can either have a row vector or you can have a column vector. So this matrix A here is called as the system matrix. Whatever the system, whatever the plant will generate is that matrix, system matrix. And whereas the B and C here are the responses to the system matrix, are the input and output matrix that are given to it. So these B and C are input and output matrix, and the D term here is the feed forward term. D is the feed forward matrix. If you go back to my previous lectures, therein I have explained you the feed forward, the open loop transfer function, and other things. So here we represent all this network in this particular form. So what is a state? See, basically it's a group of variables which summarizes the past history of the system. Now, in order to predict the future values, so we can say that in a state space variable, the state represents, it is a group of variable, it is a group of basically state variables, okay, that are required to predict the future future values future values, okay. So basically now this is the state. Now what is the state variable? I'll be showing you how we can formulate the state variable also, so don't worry about that. So when I define a state variable, basically, see the state variable, what are the terms which will be having the, that means a state is a group of variables that are required to predict the future value. So what are the values which can be predicted in the future? So that means a state is a group of variables which is having some amount of history. So if you look at the state variable cannot be any register, okay. it has to be any energy storage element like your inductor or capacitor. So state variable you cannot take a resistor because it will not be having a previous storage value. Resistor, as soon as you switch on the light, light will come. As soon as switch off, light will go. But now in case of the state variable, it is depending on the energy storage. So we can say safely say that the number of state variables required in a system is equal to the number of storage elements present in the system. So this state variable, it is equal to number of, okay, we'll go back, sorry, number of energy storage elements present in the system, storage elements. Okay, so let's move forward and let's see about the other terms. So we had already defined state variable. So examples of the state variable. See, when we are assigning state variable, so the assumption for the state variable assignment, as we'll see as we'll be moving forward, how do we assume is that we say current through the inductor. Okay, current through inductor or voltage across capacitor, voltage across capacitor. Capacitor is the state variable. Capacitor is the state variable, is to be taken as a state variable. Taken as a state variable. There is a strong reason for it. I'll show you why. The reason is that if you look at the current through the inductor, okay, so, or the voltage across the capacitor, so you're basically the current through the inductor or the voltage across the capacitor. Why they are taken is because if you look at your E is equal to L di by dt. Okay, or if you look at your I, okay, uh, I is equal to in terms of your I is equal to C dV by dt, right? So it is reverse current through the inductor. It has to be voltage through the inductor and current across the capacitor should be taken as state variable. So yeah, it's very night right now. So similarly, I'll be explaining you in the future classes. Now let's define this. So this state vector, state vector basically it's a vector which contains the state variables as elements. So we need to express these state variables in a state variable equation form. Prior to going there, okay, suppose I have expressed this voltage in form of E, so I can write my E is equal to uh, the voltage across the capacitor. If I want this voltage across the capacitor, voltage across capacitor, how do we express this voltage across the capacitor? So this V of t would be equal to 1 by C integral I dt. Okay, and if I differentiate both the terms, I get dvc by dv by dvt by dt is equal to I by t into C. So this is one of the equations. This is differentiating the voltage across the capacitor. Now, now what about the this thing from this output voltage? See, if I consider a circuit like this, okay, I have a resistor, I have an inductor, I have a capacitor. So I have an RLC series circuit. I want to write a state variable equation for this. So this is my I of t, this is my R, this is my L, this is plus minus this C. So this is my input voltage. Let me try Vi of t, and the voltage across the capacitor is my output voltage V naught of t. So if I carefully look, my V naught of t would be the same voltage. What is the voltage across the capacitor? Suppose the voltage across the capacitor is Vc of t because they are connected in parallel, so it has to be same. Now, if I apply the KVL around this loop, okay, if I apply KVL around this loop, so I get an equation for the KVL because the input is Vi of t, but this is the voltage rise, rest through this drop, this drop, this drop. So only through this there is rise. So V rise is equal to V fall. So what is the fall? If the current, suppose I take the current across this as I of t. So this would be equal to r I of t plus L di by dt. Okay, I of t, of course, and voltage is Vc of t, which is nothing but the V naught of t. Now if I want to express this in terms of di by dt, okay, on one side, and I will take the other side, so I can safely write that minus r. This you can do at home. Minus r of t, I'll straight away write minus Vc of t divided by L plus Vi of t divided by L. So we are getting this equation. Now, if I want to write this equation in a state variable form, in a state vector form, so as a state vector, I can express this equation like this. State vector, I can write this like this: x would be equal to I of t into Vc of t. So I differentiate, I take this as a state vector or the state variable, and I say that my I is equal to, and similarly, my x dot would be equal to I dot of t Vc dot of t. So when I write x dot, it means the differential thing, dx of by dt. So here I dot of t would mean di by dt, and similarly Vc dot of t would mean dvc by dt. So this is the meaning of this. Now if I want to, if you look at the expression there for x dot of t, first equation is di by dt, and the second equation is dvc by dt. So for the di by dt, so definitely I have the equation, and for the dvc by dt also I have the equation. So if you look at the dvc by dt equation and di by dc equation, if I want to write this equation, I can write it in a form. I'll take in the next slide, okay, so that you'll understand. Where's the next slide here? Yeah. So in the next slide, let me start it. So I have this equation as x, I have taken as I of t, Vc of t. Similarly, x dot I have taken as x dot is equal to di of t divided by dt, that, and this is dvc of t divided by dt. Okay, this is my x dot. Now in the above equation, I got these equations. I say safely that dvc by this thing dt was equal to I of t into c. So this is my equation one. Okay, and also I got one more equation, that was di of t by dt. That equation I got as minus r I of t divided by L minus Vc of t divided by L plus Vi of t divided by L. The same equation can be written in this form as x dot, wherein x dot is equal to di of t divided by dt to dvc of t divided by dt. That term is equal to, now this term, if I want to write what is the first term here, so you can see minus r by L is the first term here. So I can write minus r by L. And can you tell me what is the second term here with respect to this? So the second term here with respect to this is minus I by L. And what is the first term here? There is, the first term here is 1 by C, because this is basically I of t into 1 by C. There is no second term. So if there is no second term, we straight away write 0. Yeah, okay, because see, whatever is with the, see, this is like how it goes is, first is whenever we have to do any substitution, it is column as and rows. So di by dt, okay, minus r by L, okay, so minus r by L, and after that dvc by dt, this term is there, right? So with this term will go minus 1 by L. Then the second equation, okay, in the second equation you have the 1 by C term, and now you can have this variable, but this variable was attached with what I of t, right? So you have to write I of t. So see here, minus r by L into I of t, right? And then what is the second term? Vc of t, right? So if you want to write the equations here, What did I say? I say first you go about this row. Okay, here if you are going row, here if you go column way, so first equation will be minus r by l into it. The first point you got minus r by l into it. Similarly, the second point is minus 1 by L into VC of t. So if you do minus 1 by L, so you will get this point. Minus 1 by L into VC of t. Now, if you look at this equation, I of t into C. So I of t 1 by C. Okay. So again, the row, right? 1 by C. 1 by C into I of t. So you got the equation. But 0 into VC of t. So there is no value of this. So it is okay. Now we have accounted for this and these two variables, but this variable is left. Now to account for this variable, I have to, because this is an input vector, I'll write 1 by 0 into sorry, not 1 by 0 because it's 1 by L, right? 1 by L into Vi of t. Same way we'll do, okay? You can do column into row or row into column, whichever way. So you'll get the same equation. This will account for this. So this is how it is done. And as far as the output is concerned, y is concerned, you can directly straight away write your y value to from here. You can write this y value is equal to 0 into 1 into I of t, right? Into Vc of, so 0 into 1. So this term is getting over 0. So 0 into I of t, it will be 0 into I of t, which is 0. And for the first term, for the second term, it is 1 into Vc of t. So output, what is the output? If you look at the equation, if you go back to the equation, so your output is your Vc of t. So your y of t is simply Vc of t. Just you have to express in that form, state variable form. So you can write like this. So from these equations, if you have understood these equations, now I have got these matrices. Okay, so I can write the matrix. This matrix I call it as A. Okay, then this matrix I call it as B. This is my matrix C. So here the B part is straightforward term is not there, it is 0. So I can safely write that my A matrix would be equal to minus R by L minus 1 by L 1 by C 0, and B value would be equal to 1 by L 0, and similarly C is equal to 0 1, and my d value is equal to straight away 0. So this is how I have expressed a differential equation of KVL and KCL in form of state variable. Now in the next class, I will be solving some problems, explaining you the concept of controllability. And if you're new to the channel, please subscribe it. Okay. So thanks. I'll end the discussion here and the meeting here. Thank you very much.